Welcome everybody to the CDA Center for Digital Agriculture Distinguished Lecture Series. This is the third speaker in the series, and I think we have a really interesting, exciting talk lined up for today. We will be having one more speaker in the series this year, and then we will be starting with the new round of our speakers starting in the fall. But to introduce today's talk, I would like to invite Professor Salah Issa from the Department of Agriculture and Biological Engineering. Salah.
Thank you, Vikram. It's my honor to introduce Dr. John Shutske. We actually, technically, you could consider us academic siblings. We had the same advisor, while he is much younger sibling. So John is a professor and extension specialist at the University of Wisconsin-Madison. His research, extension, and teaching efforts are focused on agricultural safety, on risk control, and health promotion in ag and other closely related industries. He also serves the director for the University of Wisconsin Center for Ag Safety and Health, and is an affiliate professor in the School of Medicine and Public Health. So Dr. Shutske, he worked on design, on evaluation, on development of engineering technologies to better protect farm operations and employees from injuries and other losses. That has been his main focus. And currently, his current work is on quantifying risk associated with new driverless automated robotics and other novel agricultural equipment. And that's one of the reasons why I thought he would give an excellent talk in this series. And I'd welcome John to share his slides and get started on it.
All right, thanks a lot. So I want to begin by giving you just a little bit to let you know my title of my talk is a bit tongue-in-cheek. The technology part is easy, but what about the risk? And I'm going to give you a couple of caveats in a minute. I do appreciate the introduction. And the other person who I would really like to recognize in this talk is Kelly Sandner. Kelly was my graduate student, probably one of the better graduate students that I've ever had. I'd say the best graduate student I've ever had. She got done in record time and now has an awesome job out in industry. But Kelly did a lot of the work, a lot of the data collection that I will be talking about today. The other group that I'd like to mention, I don't think I actually have this mentioned in any slide in particular, but I would like to thank USDA NIFA for the Hatch funding that led to some of this research, and we'll be funding an ongoing graduate student starting here in the fall of 2022. So the technology part is easy, but what about the risk? Well, not really. It's not as simple as that. I would like to just start out with a few official caveats about this presentation. I want you to take that title with a grain of salt. I also want to let you know this is not going to be a presentation about programming, about machine vision or machine learning or artificial intelligence. So just start right off the bat to let you know that. I have done work in some of these spaces, including designing safety-related applications using sensors and control systems for things like human presence sensing. Also, I did my PhD work in fire protection, fire detection using a variety of different sensor categories, and also did some work back in the 1990s. I think some of the early work using radar and microwave to look at collision avoidance with farming machinery. So I'm not totally devoid of technology experience, but I'm not going to be going deep in any of those software or technical areas. I've also done some teaching in the design process. I have been teaching our capstone engineering design as part of our ABET accredited program up here. That obviously includes safety and risk assessment, and we try to follow the engineering code of ethics where safety and risk is heavily emphasized. And maybe most importantly, with my past work historically, I've investigated literally thousands of farming injuries, fatalities, and also, I think just in the case of fires, probably about 4,000 combine, tractor, cotton picker, sugarcane harvester, So if you need somebody to ever talk about machinery fires, like you could Google that topic and you'd probably find my name in there. So that's my caveat. The outline of my presentation here today is I am going to talk about some of the driving forces that are moving us towards more automation, more high automation with agricultural machinery. Some of these you've heard. I actually watched one of your previous speakers, and you're going to see some of the same coverage. I will try to be relatively brief in that. What I really want to focus on is the understudied barrier that I think safety and the safety, not only for operators, but for other people who are stakeholders with highly automated agricultural machinery. I'll talk about risk assessment and control, in particular as it relates to the many, many new standards that are coming into the marketplace through groups like ASABE and the International Standards Organization. I really want to also talk about the fact that when we talk about safety and identifying and evaluating hazards, we need to think beyond just the obstacles that we might find in a defined agricultural or farm field. Many of the standards that we are developing actually specifically exclude some of these hazards, which I think is actually maybe a bigger deal than obstacles in fields. I'll talk about some of the data possibilities for doing more robust risk assessment, and then finally wrap up by talking about some of the future research needs, and actually just kind of like foreshadow a little bit. Salah and I are planning a conference here for probably the month of November of 2022, and I'll talk briefly about that. So let's begin by talking about these driving forces. I think many of you have heard of the whole notion of having to double global agricultural production in the next, between the year 2022 and the year 2050. So that's what, 28 years. We're going to have to double production on the basis of three main driving forces. Number one is population growth. We currently stand at about 7.9 billion global citizens. That number is going to grow to something close to 10 billion by the year 2050. The other thing that we know throughout recorded human history is that as people get more affluent, as they have more disposable income, they demand a higher quality of protein. And right now that's most likely to mean animal protein. And then the final driving force is the use of agricultural products for energy and biomass production, those sorts of things. All of this is going to happen while we face these major, major headwinds of things like water, too much water, not enough water, water in the wrong place, wrong time, water quality. And a lot of our water issues are obviously being driven by climate change. And the other thing I want to just mention to you is the impact of more animals on the planet as a result of growing demands for protein also mean increased probability of occurrence of different types of diseases, emerging infectious diseases, including things like pandemics and forms of influenza. So we face a number of challenges as we grow our population and double production. Another thing right now, and I need to say this, my work is nested in Wisconsin in extension under the umbrella of farm management. And right now, probably our biggest farm management issue is this labor shortage that I don't see letting up anytime soon. Interestingly, that is a mix of demographics, changes in our rural communities, the perception of agricultural work, and also, frankly, immigration policy. So a lot of different forces there. If you look at the right-hand side of this slide, it's particularly interesting because it's not only a labor shortage on farms, but it's also a labor shortage within our ag retail space. So when we talk about automation, machinery companies, local dealerships, people who are involved in repair and maintenance and programming, and the whole suite of services that go with agricultural machinery automation, we need to be thinking about the labor issues there as well. The big driving force that motivates me probably more than anything is the notion of safety, prevention of injuries. Salah and other people are quite familiar, I'm sure, with the concept. We have a hierarchy of controls. When we look to prevent people from getting harmed or killed as a result of exposure to the farm workplace, the safety hierarchy suggests to us that the more we can do to take people out of the equation, isolate people from hazards, that would include agricultural machinery, we're going to have more success at reducing the burden of injuries and fatalities on farms. A couple things that I just want to mention to you. The National Safety Council and other sources of data suggest that agriculture, production agriculture specifically, continues to be our country's most dangerous occupation. The other thing that I want to mention to you is we oftentimes talk about farm accidents. I put that in sort of air quotes. The word accident implies something that happens as a result of chance or fate or something that's an act of God. If you look at Webster's dictionary definitions, you'll find those things. But the reality is when we have so many people being killed and injured on farms, those deaths and injuries are a result of a transfer of energy, which is really the responsibility of engineers to control and harness energy for good and to protect people from the bad aspects of it. So I think our terminology and the way we think about these issues is quite important, especially when we think about the fact that agriculture's death rate is 7 times higher than it is in all other industries combined. Another driving force is obviously the need to reduce the drudgery, and some people would call this elevating the human role. The right-hand picture, picking rock, as we called it in Indiana, for those of you who have done that kind of work, we do have a large number of tasks in agriculture that are particularly boring, monotonous, dangerous, and they are things that obviously create all kinds of hazards and ergonomic risks as well. We do need to be a little bit careful about this. I believe looking at the ethical aspects, there are a lot of considerations and what I'll call countervailing forces. One of those is the farming culture. Every farmer I talk to in Wisconsin about autonomous or driverless equipment, particularly when we start talking about field operations, tractor, forage harvester operations, there are a lot of people who still really enjoy doing that type of work. Even though some of us might view it as monotonous or boring, it is still part of our culture in many parts of the country. We also need to recognize when we look at automation that the picture that you see on the left in developing countries, this type of work that we would consider to be boring and monotonous is actually the source of employment for more than 1 billion people on this planet. So I think these are things we need to consider. We also talk about engaging youth. I know that in my own circumstance, I won't mention a manufacturer per se, but if it wasn't for my dad's green tractors, his 4020, his 4240, his 630, and his age, I probably wouldn't have gotten as involved in agriculture, and I probably wouldn't have gone on to be an agricultural engineer had it not been for the machinery that was on our farm in Northwest Indiana. So engaging youth is really important, especially as we look at continuity and succession planning. There's obviously huge capital requirements, and there's the issues of connectivity. I'm going to highlight in a moment or in a few minutes a survey that we did here in Wisconsin of over 1,000 agricultural producers. And still, even in a state like Wisconsin, we have about 20% of our farming operations that still don't have access to high-speed internet. So these are all things that I think that are going to cause some limitations in terms of the growth and kind of be a countervailing force for those forward-looking trends. The other one that I find particularly fascinating is, I'm sure some of you probably followed this over the last couple of years, and especially here most recently, John Deere has had a major presence at the Consumer Electronics Show. If you've ever attended that show, in most years, pre-pandemic, we're talking like 120 to 140,000 people, but the focus has almost always been around consumer electronics. I mean, that's the name of the show, and yet John Deere is really moving toward educating the public, highlighting, creating excitement, as are other companies like C&H, who released their autonomous tractor concept vehicle at the Farm Progress Show, which I think was back in 2016, if I'm not mistaken. I think I first saw that machine in either Decatur or over in Iowa at the Farm Progress Show. So a lot of attention is being paid to autonomy. And I know that that's been one of the focuses of this series. And again, Salah, I appreciate you inviting me to come in here today and talk. As we transition towards looking at safety, I'm going to argue that this is an issue or a need that has been relatively unstudied and undocumented. We've done a lot of research in places like Wisconsin. Before that, I spent about 17 years over in Minnesota working with injury epidemiologists, doing these really deep dives in literally looking at thousands of farm households and documenting their injuries and their other types of health and safety related issues. But most of that work has been looking backwards in time, obviously. And when we look backwards in time from now, or from a lot of the work I did in the early 2000s or even in the 1990s, we're often still looking at old machines that may lack appropriate protective equipment, shielding, and those kinds of things. As we look forward, there are not a lot of people around the country who have been studying and looking at these issues of safety and risk with new equipment. When I first began to write my Hatch project proposal, I think it was in 2017, I was pretty excited as I was doing Google Scholar and other searches to find a chapter, supposedly a chapter in this book called Agricultural Automation. And there was to be a section in here on safety. So I got this book. I waited actually quite a bit of time to get it from CRC. And when I received the book, this is the coverage of safety in this book. There's literally one paragraph, it's actually one sentence in the chapter on vehicle robots by author Noguchi, who says, if the robot must take full responsibility in the unlikely event of an accident, it will lead to enormous cost increase and hinder the progress of robotization. This was the entirety of the coverage in that particular article. And even this, to some extent, there are a number of things here that I think deserve more conversation. First of all, the concept, if a robot is to take full responsibility. Well, first of all, yes, absolutely. The robot may not have to take responsibility, but certainly the manufacturers, the designers, the engineers, the engineering design teams, all people who are part of the supply chain, including dealers and service people, there will be responsibility when things begin to happen as a result of automation. The other thing I have highlighted here is this statement, in the unlikely event of an accident. I don't want to provide an opinion on the likelihood. We really don't know at this point. And that's one of the things that I want to talk with you about here as we look at things like standards and risk assessment methods. We really don't know the likelihood or the probability of these kinds of things happening. And you'll see why that's important here in a few minutes. I will agree that there will be a cost when injuries and incidents begin to happen. And in fact, yes, these safety related issues could hinder progress. I personally believe that safety and the confidence of not only the public, but definitely owners, operators, employees, people who are stakeholders, absolutely is going to be a driving force. And yet, again, as I suggest, it's something that has just not received a lot of attention here over the last many years. If you look at some of the things that have slowed the progress, like with autonomous vehicles on highways, there have been a couple of fairly significant events involving Teslas, unexpected events that could perhaps now, looking back retrospectively, could have been preventable. This particular one is causing some issues with NHTSA, National Highway Traffic Safety Administration, 354 complaints of random braking. When we look at the regulatory issues, right now, there are not a lot of regulators that are paying attention to autonomous agricultural equipment. The one exception is California, where we are facing some major challenges. I don't want to quite say a stalemate, but I know that the industry is quite concerned about the direction that California goes. And part of why that's so important is because California is our biggest agricultural state in the country, and probably globally as well, a major, major factor. And I'll come back and talk about that in a few minutes. But again, OSHA being an occupational safety organization, safety is kind of front and center in terms of their ability to adopt these pieces of equipment. I also want to just briefly talk about on the side of policy, politics, and communication. In terms of looking at state legislators, in terms of looking at federal regulators, there's obviously a lot of attention being paid to motor vehicles. But I know that even here in Wisconsin at the state level, even with motor vehicles, which might be some of our first uses of these technologies, that'll be commonplace. It's something that we're just really beginning to look at as a state. I talked a little bit about the California experience, where actually the driving force with OSHA is really labor. And I think really the concerns that are driving it are about the potential displacement of labor. And then again, I talked a little bit about some of these high profile events with Tesla. This one in particular is of interest to me, a Tesla vehicle using the Smart Summon feature, which basically says I can push a button and have my car come to me wherever I'm at. A person that was coming out of a private jet, $3.5 million private jet, he used his summon feature. The Tesla came. You can watch the video. The Tesla basically took out the jet, creating, again, some perception problems for the industry. The thing that I think is really important is that these groups who are stakeholders, regulators, legislators, people who work in the insurance business, they tend to be a really risk-averse group. So any type of safety-related issues that occur are probably going to disproportionately sort of slow the progress and slow adoption. There will be safety-related pressures that actually are actually as a result of other things, for example, this whole idea of labor concerns. So that's kind of the context and background of why I think we need to be looking at safety. What I want to do now is to take a deeper dive at how we and how the industry is approaching making this new equipment as safe as possible, reducing some of these barriers, hopefully at least not creating barriers that slow the progress of future adoption. The first one of these that I want to highlight for you as kind of a baseline, kind of a foundation for any safety efforts in the engineering profession, and that's the whole notion of engineering design standards. I'm guessing that there are probably a number of you who are watching this who are quite familiar with design standards. If not, very complicated. If you look at this whole space of autonomous equipment generally, a number of different standards, and I've got the standards here for earth-moving machinery, mining, robots. This is kind of going clockwise, starting in the upper right-hand corner, industrial trucks, cars, railways. And you can see now that even in the space of tractors and agricultural machinery, there are a number of standards. I only have a few of those listed. We're actually in the process of beginning to inventory all of the things that are out there, paying close attention as these standards get developed, how they can be developed more effectively, how they can be improved. Some thoughts about standards, and safety as it relates to autonomous equipment. Number one is that standards in engineering are developed through what we call a consensus process. The idea of a consensus process is that anybody who would be considered a stakeholder, from the original design engineer who envisions a product all the way to that end user and everybody in between, people involved in financial decisions, insurance companies, again, the end user, workers, dealerships, people involved in maintenance activities, all are considered to be stakeholders. So just a huge amount of activity. These standards, if you've ever dug into the details of an engineering standard, and I do this with my engineering senior design class, they're extremely thorough. They're extremely complex, but they also have to be written in such a way that they cover the whole spectrum of possible design alternatives and applications. And so finding content within a standards that apply to my specific application or some unique feature of my product in some cases is very difficult. They're also very densely written, and as a result can be relatively hard to apply. And for those of you who are interested in outreach, extension, professional development for engineers, I think there's a whole range of different opportunities to better apply these new standards to the autonomous equipment space. The other thing that I want to just talk about briefly is that most of these new standards that are coming out rely on risk assessment methods that include, but are not limited to, these two. One is failure modes and effects analysis, It's a method that's been around for decades. And the other one is called HERA, which is quite similar. HERA is hazard analysis and risk assessment. So these are kind of the foundational bedrock within standards that are the building blocks for safe design of equipment. So what we wanted to do in our work, I'm just going to pause for a quick minute. I see there's a few chats. Okay, I think we're good. What we wanted to do in our work is to learn more about what is industry doing to use these tools, to use engineering standards, and then really like how are they thinking about these multitude of risks that are present as a result of their design work with automated agricultural machinery. We started out by doing a survey, IRB approved, so that we could protect the privacy and anonymity of individual engineers who might be working for companies or private sector firms. We identified a roster of 706 potential respondents based on ASABE, American Society of Ag and Biological Engineers, and their committee rosters. We looked for people in groups and committees that would be likely involved in design work with fully autonomous equipment. We designed it in Qualtrics, obviously mobile friendly, which we've learned that a lot of people who are taking surveys are using their phones to do so. And we asked about their efforts in risk assessment with both highly automated, or what I'm going to call HAM, highly automated agricultural machinery, as well as traditional, either non-automated or less automated. Our response rate was relatively low, and part of that was we identified a lot of people in our initial 706 who were either academics, who were doing teaching work in this area. They might be doing some level of research, but were not directly involved in the design activities that we were going after. But our total response rate was about 18%. We did note that of those people who provided us with informed consent, that they were willing to participate, that they in fact qualified in some of these areas. Of the people who started the survey and provided consent, about 74% of those individuals completed the survey. So these are some of the data. This is, again, the work of Kelly Sandner, who based her master's around this and the other part of this project that I'll talk about. We learned that, yes, some of the people who are out there designing equipment in the autonomous space are using some of the necessary standards. This series that you see, ISO 25119, it's actually a 4-part standard, extremely thorough, it's also very new from 2018. About 35% of the people were using that standard. The other thing that's interesting is the heavy use of standards 12100 from ISO and also ASABE 318.18. ISO 1200 is the general safety of machinery, the general principles of safety in the design, including risk assessment and risk reduction. And those techniques employ failure modes and effects analysis. Again, you're going to see why that's important when I come back to it. Interestingly, ASABE 318 has been around for several decades, even before automation and highly automated equipment was a glimmer in some engineer's eye. So it's very basic and it covers the basics of agricultural equipment. So what's most interesting is the two most commonly used standards don't even necessarily apply specifically to highly automated machinery. There's another one that was mentioned, I think used in about 15 to 20% of the instances, and that's this ISO 26262. The other thing that we looked at, and again, I'm going to come back and show you why this all kind of fits together and why it's important. The other thing that we wanted to look at is, okay, if you're part of an engineering design team, what are the actual methods that you're using to assess risk? We looked at low or non-automated machinery, as well as highly automated machinery. And with both groups, the most commonly used techniques included failure modes and effects analysis, as well as informal group analysis or brainstorming techniques, which is essentially a group of design engineers sitting around a table and envisioning all of the possibilities, all of the ways in which a machine could fail, in which an operator could perhaps interact in an unsafe manner with a piece of equipment, and then again, taking the appropriate mitigation steps to reduce the risk associated with those types of events. Some thoughts on all of this. And again, the sort of driving force for the research that we have been doing is with highly automated agricultural machinery, FMEA is still widely used, though less so compared with non-automated design. The other one that is used quite frequently is called hazard analysis and risk assessment, or HARA. And another one, even yet in that data from the previous slide that I just showed you, is called fault tree analysis. Fault tree analysis assumes that we know of a type of incident or catastrophic event that could occur, kind of a top-level event, an unexpected or an undesirable outcome. And then we kind of work backwards to look at the systems and subsystems that could fail, ultimately leading to that top-level event. And what's important about all of these techniques that are being used and that are also being advocated within these standards is these techniques rely on known estimates or the ability to use previous historical data to estimate the probabilities, the severity, and the detectability of these hazards occurring. Hazards or failures or inappropriate ways in which human beings might be interacting with this equipment. And so it's pretty obvious then, logically, if you're basing your risk analysis techniques on historical data, anytime that we move into a new paradigm, like fully automated agricultural equipment, we have some real gaps in terms of our knowledge. By the way, the idea of detectability, which is really crucial to the equation that helps you develop a risk profile for a particular piece of machinery, detectability is how hard is it to sort of detect or notice that the hazard is present? What's really important about this is that in software, in many cases, those failures that could lead to some type of event are almost 100% undetectable. So it almost, blows apart these equations for doing quantifying risk estimates for these new forms of equipment. And again, these are the tools and techniques that are embedded in these standards that are coming out and becoming the foundation and the building blocks for engineers. So at the same time, I'm being critical. I'm saying, okay, these standards rely on these old risk assessment techniques like FMEA and HARA, but at the same time, we need to start someplace, right? And so that's where this idea of brainstorming comes in. Engineering design teams coming together, talking about the possibilities, using what historical data we do have at our disposal, and then basically beginning to put together these risk profiles based on that existing information. Again, as I'm going to say, applying standards and actually putting these ideas and concepts embedded in standards into practice is a big challenge. It's a practical challenge. It's also just simply an information overload challenge. I'll also say that other industries, in particular motor vehicle design, is probably going to be quite a bit advanced from where we are because they have had a chance through the slow introduction and integration of some of these highly automated features, even starting with things like cruise control or automatic braking systems or forward-looking radar. They have had the ability to begin to collect some of these data points that allow them to more easily predict risk. I think what's really important for those of you who have students who are thinking about risk, who are thinking about the possibilities for misuse or failure, a lot of it is often been about using our imaginations. You may remember after the events of 9/11, now more than 20 years ago, we talked about that as being a failure of imagination. As we looked at the potential threats from terrorism, we didn't necessarily think about flying jet airliners into tall buildings as a potential mode of attack. So I don't want to underestimate or appreciate the value of teams working together and thinking about risk from that perspective. However, we felt that it was important to bring additional data to the table. So I want to talk about a second part of Kelly's work, and that is using a data set that we call FACE. FACE is the Fatality Assessment and Control and Evaluation Program, which is funded by NIOSH. For those of you who don't live in the safety world, NIOSH is the National Institute for Occupational Safety and Health. NIOSH has historically funded a large number of states to do detailed on-site investigations of farm work-related incidents and accidents or events, in particular fatal events, and probably have the most sophisticated and complete and really highly detailed set of data that's available. But to my knowledge, has never been used within the space of this whole idea of assessing risks and thinking about the possibilities. And again, imagining the potential for misuse and failure. We ended up looking, because of the interest that we had in autonomous tractors, we ended up parsing through about 450 total FACE records. We extracted 248 tractor incidents that had occurred from 1990 to 2020, so a 30-year project period. We wanted to figure out what might we learn from this data that could be useful in the autonomous space. And again, how might we think about using some of this data to better inform design engineers as they evaluate risk? And then also we wanted to look at maybe some other potential sources of data that would allow us to fill in some of the gaps and some of these needs. I'm going to go through this rather quickly. Our tractor analysis found that 61% of the report, 61 or 25% of the reports of tractor-related fatalities involved environmental factors, wet surfaces, undetected obstacles. 130 or more than 50% of our reports involve some sort of sloping terrain, involved from large hillsides to even very minor slopes. 85% of the deaths on sloping terrains involved an experienced operator. That is, an operator who did have experience. And though the majority of operators were considered by FACE investigators to be experienced, 92% of those incidents were deemed to have been a result of an erroneous decision, either a decision that was made incorrectly, one that underestimated risk, or perhaps did not perceive the relevant hazards that were located in the environment. So the idea here of looking at this FACE data, actually twofold. First of all, we know from just this little analysis of these 240 incidents, highly automated machines must incorporate systems and components that are at least, if not more accurate and dependable as compared to a human, experienced human operator. Because we know that even experienced human operators will fail and will fail to perceive some of these hazards in the environment. We also felt like, after looking at this data and really parsing through it in great detail, that the FACE data possibly could be used to bolster those imagination-provoking design team conversations that are used to identify, evaluate, and mitigate risk. And then probably most importantly and most exciting, and where we probably will go forward with this, is that we could potentially use FACE data and other similar data sets that are out there to inform, again, to inform these conversations, but possibly also to inform machine learning, inform artificial intelligence through training sets and other products that are being developed. Why not start with a robust set of data that's out there, that's free? So Kelly did, in her work, put together what we call a scenario generator. I'm not going to spend time showing or talking about that, but it would allow somebody to parse through the data to give the software a set of conditions and then spit out a series of scenarios that could be used in the planning process. To summarize this work, and then I'm going to just take a little bit of a pause and see if there are any questions. From Kelly Sanders' work, we learned that industry people are, in fact, using standards, old standards and new standards, even though they are difficult. The standard scene is evolving quickly. It's really difficult to keep up. The resources necessary to keep up are significant. And one of the concerns I have is if you work for a large multinational machinery company, your access to standards and your ability to use standards, you probably have a full-time staff of people who just focus on standards compliance and standards development. Smaller companies that are in this space, and there are a lot of them, as you guys know, probably maybe not even be aware of standards, and if they are, perhaps lack the resources to be able to use these tools effectively. Standards continue to push these ideas like HERA and FMEA. However, again, my point in all of this is those techniques advocated in standards rely on past and historical data that we don't have with these newer forms of machinery. However, at the same time, we feel that we can use some of these existing data sets to actually do these tasks and perform them effectively. One last thing before I open it up to some additional questions and also talk about some more issues that we've identified. Our work has focused largely on larger machines. The risk assessment for smaller machines like swarm robots and other swarm types of machines will necessarily be different. And from a safety perspective, might actually provide some improvements. You have less mass, less velocity, so we're talking about less kinetic energy. In the case of many of these machines, they're going to tend to be probably a little bit less complex. We also know that if we have multiple machines out working in a field, there's less downtime risk. I'll talk about downtime here in a moment. And there may be other production benefits that also reduce risk, like less compaction, as an example that's commonly cited in the literature. Also, our current emphasis has largely been on safety during field operations. And that, again, is a little bit limiting, as I'll talk about here in a moment. The standards that we have reviewed largely focus on obstacle detection in a relatively defined, secured field environment. But I believe we need to begin to think beyond just that isolated field. With that, I've got this last bullet that says, but what about? I'm going to pause there for just a moment and see if there are any questions or comments. And then it might also give me a little bit of an opportunity to take a drink of water here. So there is a question. I'm surprised that risk level depends on detectability. Couldn't a non-detectable error or risk or failure still be risky? Yeah, so what's really important about FMEA is if something is highly detectable. When I teach my senior design students, I use an example. I used to have a moped that I would drive around on campus. If I can look down at the front forks and the front wheel of my moped and I see that it's wobbling and the bolts are loose and I'm about ready to lose a wheel in the front of my moped, that is something that is very detectable. So there's actually less risk there because when I see it, when it is more detectable, I know that something is wrong and I need to make a fix. I need to make a change. Whereas something that's happening that is invisible to me, whether that's a software failure or a mechanical failure, if it is not detectable, it is going to be considerably more risky. And the same concepts apply with HERA as well. I have just a few more slides in this whole idea of, but what about? So let me talk about this briefly. But what about environment? So when we talk about obstacle detection in fields, relatively easy to do, right? I mean, if we have a large, regardless of the size, a rectangular field with clearly defined boundaries that's flat with no sloping surfaces like we found in the face data, probably not a big deal. But anytime we move beyond that less than ideal, we do have potential problems. I've had some questions about our face data. Our face data was largely about tractor rollovers. And people have said, well, it's good if we pull people off of tractors and we have highly autonomous tractors that are pulling spray rigs, spreading manure, doing tillage or planting operations. If it rolls over, like from a safety perspective, not that big a deal. Well, what if that tractor, what if that machine is carrying a load of fertilizer, a load of manure, a load of chemical? Obviously, we have environmental risk. Unfortunately, the existing standards that are being developed in many cases specifically exclude environmental risk. The other thing that I'm just going to say is if I'm going to go out and spend $1.25 million to buy a new tractor that's fully autonomous, the last thing that I want to have it do is roll over in a field. because we're probably talking about hours, if not days of downtime. So even when you pull the equation, the human being out of the equation, some of these things are problematic, even though we may not injure people. Similarly, the existing standards that are being developed exclude the impact on animals, livestock, wildlife. So I think some gaps there that we need to be thinking about. We also know that when injuries occur on tractors and other types of machines, they often occur during what I'm going to call non-routine circumstances or situations. When I did a lot of this work back in the 1990s and I would talk with farmers, they'd say like, yeah, a lot of times when I've gotten hurt, I'm just kind of out, the term was mucking around. I'm out repairing something, or I'm out taking a part off, and I end up with a severe eye injury, or I fall while mounting or dismounting to perform a repair. So obstacle detection is one thing, but we also need to be thinking about what happens in terms of safety and risk when people are involved in some of these other peripheral, non-routine circumstances and situations. Another thing that I think we need to look at even more closely, this is where I did my PhD work. I looked at about 4,000 tractor and machinery fires, and we looked at sensors and detectability and automatic suppression systems. Again, if I lose a $1.2 million machine that is out fully operating by itself to fire, this is definitely something that we need to be thinking about and considering in the risk assessment process. And the other big one is downtime. Again, if we're going to give up a traditional set or a set of machinery that's used for a row crop operation, or here in Wisconsin, we're heavily into corn silage and hay production. If we're going to move towards autonomy, we need more assurances that downtime is not going to be an issue. Even with traditional equipment, the loss of a day during critical planting seasons or harvest seasons can run into the thousands of dollars. And if we have downtime as a result of software failure or hacking or just basically a malfunction of the machine, it is a risk that I think we need to much more thoroughly consider as we do this type of work. Another one that I just want to talk about briefly, I've had some experience looking at data security, privacy, data protection. We did a big survey of about 1,200 producers in Wisconsin. This was published in 2019. And the biggest barrier that was identified by producers for the adoption of new technology on farms was safety and security. You can see here privacy, security, ability. Another one is the ability to keep up with technological change. So when we talk about farmers investing in high tech, investing in highly digital, highly automated equipment, it is going to change the nature of the type of producer we see, their comfort level with technology. The cost, I think, is a big factor. And in this work, when we looked at the issues of safety and security with growers and producers and dairy farmers, we didn't even want to bring up the idea of software failure or of hacking. And obviously there are safety and security concerns in terms of intentional as well as unintentional impacts on software. So where do we go with all this? Again, on the safety side of the equation, there is a flurry of activity nationally and internationally. Obviously, industry knows safety is a key. And if we don't figure out some of these questions, if we don't get answers to some of these questions, we are going to be somewhat limited. Again, as I've tried to stress with you here today, engineering standards are very necessary, but they do need to be applicable. They need to be usable. Right now, it is like a massive jigsaw puzzle, quickly evolving, something that I think is going to present continued difficulties for the industry, especially small industry players that don't have the resources to actually fully utilize standards. And then finally, I think that there are new methods needed for risk assessment where we're trying to predict probabilities and severity. So I think as we begin to see these types of applications move out into actual use, we need to figure out, are there ways to share incident data? Perhaps public-private partnerships where we maintain the privacy of individual companies and individual operators who are hurt or injured. I think we can also use existing data streams. The FACE reports are one. Another one is a group called Ag Injury News, which is maintained out of the Marshfield Clinic up at Marshfield, Wisconsin, the National Farm Medicine Center. And the other thing I think we might be able to use down the road is Twitter or other forms of social media, where we might be able to use long-term streams of data for surveillance of events, but also possibly predicting or anticipating events that might occur in the future based on data that's presented by users of the equipment and also potentially manufacturers. From Kelly's thesis work, we talked about the development of standardized training sets for artificial intelligence in agricultural machinery. I think it's quite possible to use some of these data sets that are already out there to help us with like the scenarios that we talked about, developing risk assessment tools that quantify risk based on varying levels of highly automated machinery. I've really only here talked about like fully autonomous versions, but there will be a whole spectrum of automation applications. Also developing software that references a machine's surrounding environment and conditions, and then examines those against historical reports and makes decisions in real time. For example, is machine X currently operating in a situation that looks like an old event from event Y from the FACE data, and can we learn from that sort of on the go during field operations? Again, I think we need to amend existing engineering standards to include maintenance, transportation. Transportation on public highways is something I haven't even really talked about. Also, startup operations, as well as risk to the public, fire, as I talked about, livestock and wildlife, infrastructure, and the environment. Just as a little bit of promotion here, we do have some next steps planned that are going to look at a lot of these different issues that I hopefully have been able to identify and explain a little bit here today. We are, Salah and I are working together. Salah is actually leading an effort where we'll be doing a symposium early winter, late fall, probably with around 50 to 100 people, all of the different stakeholders, researchers, regulators, insurance companies, especially the ag machinery industry. And we hope to really look more fully at these issues, identify next steps around issues of risk and safety, standards, how can we do a better job, regulation, policy, effects on the workforce. Again, the training needs, the impacts on economics locally in communities, the workforce needs in terms of training, investment in education, dealing with people who might be technologically averse to actually adopting, and then again, prioritizing things from a research perspective. So I believe that is my last slide, and I would be happy and even thrilled to take questions and comments you might have. I did provide, by the way, I provided my email address on the previous slide and on this one. And again, I just want to also recognize my student, Kelly, for all the great work that she did. Salah?
Thank you, John, very much. And to give people time to enter questions, let me just ask you, well, actually, pointed question. I don't know if you've heard in the news recently where they were saying that Russian forces in Ukraine stole $5 million worth of tractors and equipment from I think it was a facility, but the company that owned all this equipment bricked all the equipment so it could not be used. And that was really interesting to see that they could do that, but then made me also wonder the chances that breaking could happen on our farms or our locations and stuff like that.
Yeah, I think that's a big concern of industry. The potential to disable or delay something, or the potential to cause a tractor to run out on a public highway, or to basically just totally lose control of it. I think that is something from a security perspective that might be bigger than any of the other risks that I talked about, largely because that could lead to public harm. It could include harm to an owner operator, or a person who's providing maintenance activities. So I think that the software security piece is one that's really, really important.
Do we have any questions from the audience? And I believe you can unmute also to ask a question directly.
Thanks. I do have one question, which I put in the chat earlier. So, John, you said the risk level is determined by 3 factors, and one of the factors is detectability. I was quite surprised because it seemed to me, at least, that an undetected or a difficult to detect error or failure does contribute to risk, and in fact, even to damage if but the damage is detected.
So actually, it's, I guess if something is highly detectable, it's gonna lower the risk level. So it's inverse. Something that's highly detectable is inversely going to contribute to that equation.
I see.
But the idea of failure modes and effects analysis, just really quickly, is to say, okay, we have a system. What are the 100 ways in which it could fail? And then with each one of those failure modes, what is the probability of that event, that failure event occurring? If it occurs, so if that number's high, your equation is going to start high. Is it severe? Well, if the result of encountering that, is it going to be a fatality? You're going to have a high number there. If it's, I'm going to lose a half hour's worth of downtime, you're going to have a lower number. And then again, detectability, something that is highly detectable is going to lower that overall equation, the number that results from that overall equation. Mm-hmm. Something that is indetectable or invisible is going to increase the risk level. Mm-hmm. HERA is quite similar. But the idea is that both of them are predicated on this back historical data that we don't currently have.
Yeah. I understand now. I didn't realize it was inversely proportional to detectability.
Yeah.
That makes a little more sense, yeah.
Matthew, do you have any questions?
Yeah, I had a quick one. I'm going to have to run in a second, but that was really interesting. We've talked quite a lot about this risk analysis in a number of ways related to cyber vulnerabilities in ag equipment, which you touched on. But something you didn't touch on as much, where you mentioned the Tesla crash, but the relative risk profiles of some of the newer ideas in agriculture, such as the use of small autonomous robots instead of large equipment.
Right.
I wondered if that's something you'd looked into.
I touched on that briefly at the end. I think obviously from a safety perspective, well, human risk, again, if we think about the importance of energy, kinetic energy, something that's smaller is obviously going to present less potential for injury. If you get something that's small out on a public highway, actually a smaller piece of equipment is less likely to be transported on a public highway. So that's a way to reduce risk. And then especially on downtime. I mean, if I've got 7 machines out working and I have one of them that goes down, that's a way to also significantly mitigate risk.
Right. I mean, I guess what I was thinking is in terms of the downsides, though, you have more small robots. So the risk gets multiplied by the number of robots you've got.
Yeah.
And as we're talking about getting these robots to do more useful things like sowing seed or putting down fertilizer, the robot itself may not have a huge mass, but it can be carrying a significant mass of seed or other product. So, and the safety features you're going to put on that are probably going to be lesser than you'd put on a tractor or a harvester.
Yeah.
So I'm wondering if anybody's developing standards for this, or if this is the Wild West right now.
So the standards more on the small platform robots. Yeah, there are some. Kelly and I did not look into that in great detail. My next graduate student will probably be looking at that. And some of the trade-offs of different types of systems will probably be another part of what she looks at. She's also, I said, I'm not a programmer, I'm not a software geek. She is. So we may also be looking at the potential to use some of this historical data to be able to make real-time decisions out in the field, like I talked about there at the very end.
Yeah. I'm just, you seem very upbeat. I just wondered if that was because you seem very downbeat on the autonomous vehicles generally.
Oh,
so
yeah, no, that's not my intent. I mean, if I could go out and buy one of these new Deere or CNH machines and tinker with it, and my mom still owns 99 acres of land, I am a geek. I would love to have the opportunity. I also think it is something that we're moving quickly towards a marketplace. And I think, as I showed in that one book on ag automation, it's like, oh crap, maybe we need to start thinking a lot more detail about some of these safety and risk related issues. And what I try to encourage with my engineers who I teach in the classroom is it ought to be from the very moment you conceptualize an idea, risk ought to be at the forefront, not only human risk, but some of these other economic and downtime and things like that.
Thank you.
Thank you, Matthew. Appreciate it.
I think since we're at time, this is probably a good moment to segue.
Okay.
And just thank everybody.
Okay. And Salah, I appreciate being able to work with you. Thank you for the introduction. And I hope that perhaps some of you are able to attend the symposium or conference that we're working toward at the latter part of 2022.
Yes, it will be November 2nd and 3rd. So just mark your calendars, and I'll work with Vikram and the rest to.
Yeah, Salah, we should work with Melanie for sure to advertise it on the Digital Ag mailing list here. I think it reaches a lot of people, so that should be a good place to advertise it.
We plan to. I'm already working with her actually.
Thanks, John. I really enjoyed the talk. It was fascinating. Thank you.
Oh, thank you very much. I appreciate it. And thanks for those of you who hung on until the end here. So I appreciate you as well.
Bye-bye.
Bye, guys.
Thank you.